Okay, in this presentation we are going to look at fitting linear and polynomial models to data. So an insurance company wants to study the association between the number of years their clients spent in education and their claims amounts. Okay, so data from 25 randomly selected claims are contained in the file amountyears.rdata, and they comprise the two following variables: claim amount, the claim amount in British pounds, and education years. This is the number of years the client spent in education. Just think about that variable for a second. Education years, the probable set of values is between 8 and 16. Okay, so plot the claim amounts against the years of education. B, a statistician suggests fitting a linear model to the data. Fit the linear model to the data. Plot the regression line by adding it to the graph from exercise A. Okay. Another statistician looks at the plot in exercise A and suggests a non-linear relationship. Fit a model with a quadratic term added to the model fitted in exercise B. So linear model in exercise B and polynomial model or non-linear model in exercise C. We're going to add a quadratic term, so hence the term polynomial model. State the equation of the fitted model. Okay, that's the one from C. Comment on the suitability of the quadratic model in exercise C. Compare it to the model from exercise B based on the output from exercise C. So essentially just compare the two models. So we're given two data sets to work with. They are two vectors stored in this R data file. So this is material that accompanies the exam scripts. Amountyears.rdata, and I have it stored in a folder called stored data. Okay, so I load that, just specifying the folder that it is saved in. And what we're going to do is have a look at the two objects, the two data sets. So there are two vectors. It's not a data frame, it's two distinct vectors. Okay, two distinct objects. Claim amount, length of claim amount, 25 items, 25 elements in that data set. Okay, quick summary there. Have a look at the maximum and minimum value. Nothing really stands out there. Okay. Likewise, we're going to do the same for education years. 25 education years, which is 25 people, so to speak. And that is the range of values there from 9.1 to 15. Okay. So plot the claim amounts against the years of education. This will produce a scatter plot showing the relationship between the number of years in an education and the claim amounts. So just very importantly, it's always important to provide informative annotation on the graphs, which is to say a label on the x-axis, a label on the y-axis, and a title, main. Okay, so xlab, ylab, and main. Just additionally, I'm going to create the plot characters as blue spheres or blue orbs. You'll see that now in a second. So I'm going to have my x variable as education years, my predictor variable, and my y variable, my response variable, as claim amount, just to see how that works. I'm assuming that is the causal relationship. Okay, and let's have a look at that plot there. So I could have made those little plot characters a little bit bigger, but I think you get the idea. So again, we have the title and the labels on the x-axis and y-axis, so that's good enough. Okay, so what I'm going to do now is fit a linear model and plot the regression line. So we're going to fit a linear model. We're going to call it M1 for the linear model, and we have a polynomial model coming up. Claim amount, that is our response variable, our y variable, and education years, that's our x variable, which is our predictor variable. So LM, y explained by x, claim amount explained by education years. Okay. So before we continue, I'm just going to make a quick remark that we are looking specifically at the R-squareds here when we're going to compare and contrast this model and another model that we're going to see shortly. So essentially what we're going to be looking at is the output, and we're going to be looking for multiple R-squared and adjusted R-squared. Okay, both provide insights into the goodness of fit of your model, but there's a key difference. So multiple R-squared measures the proportion of variance explained by the model without considering the number of predictors. That's important. Adjusted R-squared, this adjusts the R-squared value to account for the number of predictors, providing a more accurate measure of model fit. especially when we are comparing models with a different number of predictors. That's going to be the case in this instance. Okay, so just have a quick look at the model here. So I'm just going to have a quick inspection of it here. The coefficients, this is the coefficients of our model. Just to remark that there is the intercept and one predictor variable. Okay, so disregarding the intercept, there is one parameter there. Okay, and when we look at the summary of the model, summary of M1, which is on the next slide here, this is our output here, but importantly, I'm looking at the second last line where it has multiple R squared 0.3544 and adjusted R squared 0.3263. That's not great. You notice though that EducationYears is significant, so there's something going on there, but this model is not great, really. Okay. So what we're going to do now is plot the regression line. So essentially, I'm going to work with the plot I've just created already, and I'm going to make one additional enhancement. I'm going to put in abline, or basically draw a line over it using abline. M1 is the model object, but essentially what's going to happen here is it is just going to extract the coefficients, the slope estimate and the intercept estimate, and use that to create a line that we're going to superimpose over the plot. And it's going to be a red line, and it looks like this. Okay. Well, there's something going on there, that's for sure. So, but can we come up with something better than that? Let's see. This is all part of the fun of regression modeling. So, just before I continue, this is an important function to know when you're going to be working with polynomial or quadratic terms in regression. The I function in R is used to inhibit the interpretation or conversion of its argument. It's often used when you want to indicate that certain values should be treated as is without being altered or evaluated by R. Okay. In model formulas, which is what we're going to be using it for here, it is used to indicate that an arithmetic operation should be performed directly rather than being treated as part of the model structure. So essentially tells the model carry out this calculation, okay, and don't try and do it any other way. Just carry out the calculation as is and do it right here, right now. Okay, so what we're going to do is fit a quadratic model. So this is exercise C. This is the second statistician. So it's the same as before. M2 is a linear model with the ClaimAmount, which is our response variable, explained by the predictor variable EducationYears and EducationYears squared. So the I term there is just to actually create a squaring of EducationYears and to evaluate it immediately. Okay, so it's one predictor variable, well, it's actually two predictor variables essentially in the respective number of parameters, but it is not, it's just to sort of use the first term there, EducationYears, to create the second term. Okay, hence the importance of using I. Okay, but it is a polynomial model, so there are two terms, and we're going to see that shortly. So here is the summary of the quadratic model, and you sort of see that now we have two parameters, EducationYears and EducationYears squared. Two predictors, I should say. And when we run the summary of M2, this is what we get. And again, we are looking at the second last line, multiple R squared. 0.5127, that's multiple R squared, but adjusted R squared is what we are particularly interested in this instance because of the different number of predictors, the different number of P. So adjusted R squared is 0.4684. That's an improvement over the linear model. Okay, so that says that the polynomial model is doing a better job. There we have the coefficients there again. Okay, now what I'm going to get at here is that we are going to try and create a plot that uses the quadratic model. It's not part of the question. It's actually quite complicated, but I think it's very interesting. So I'm going to sort of do it as a little add-on. So anyway, sorry, just to sort of remark, the state the fitted model, okay, for the polynomial regression. So that's it there. claim amount equals 609,272 minus 9,000 or 95,999 times EducationYears. I just sort of wrote it like that just to make it, squeeze it in a bit on the page just to make it readable, plus 4,371 times EducationYears squared. Okay, that is the state the equation of the fit and model. That's the answer specifically that you are being asked, and that is just based on those numbers there, coef of M2. So, comment on the suitability of the quadratic model. Well, the quadratic model in exercise C looks more suitable than the linear model in exercise B. The adjusted R squared has increased, indicating a better fit to the data. Okay. Additionally, the coefficient of the quadratic term is significantly different from 0, suggesting that the inclusion of the quadratic term captures the non-linear relationship between EducationYears and claim amounts. I'm just going to zip back here for a second just to sort of see that there's a little star on the right hand side between each of the terms, which is a very positive sign. So it does sort of say that all of the terms are statistically significant. Okay. Now, one last thing, I'm going to fit a polynomial curve. Okay. Now, this is actually tricky. Okay. And the reason is that if you do it directly, you get something that's very jagged if the data set is not sorted. Now, you can usually sort it if it's in a data frame, but that's not the case in this case. So what I'm going to do here is sort it by index of EducationYears. Okay. So essentially, I'm going to sort the EducationYears. Okay. So it's a ever increasing number of values. Okay, so it's sorted. But what I want to do there is get the index of each of the sorted values. So 1 is lowest, 2 is second lowest, etc., etc. You notice there down at the bottom we go from 8 to 12. This means that the raw data set is not in order. But you want to sort of keep it consistent between both data sets. So you can't sort one data set without sorting the other data set. So that's very important. So you have to keep track of the indexes. So this is a little bit complicated, and it's really just to sort of want to just add it in to see if you're really, really interested in it. So essentially what you do here is sort it, but you return the indexes and you extract those indexes. So what we're going to do is superimpose a plot over the scatter plot based on the predicted values of M2. Okay, so the response is the predict of M2, but we're going to have them sorted in a certain way, and that sorting is facilitated by IX. So the fact that they have the IX at the end of them just sort of means that they are sorted according to this system, which means it's the same in both cases. That means it will be consistent right across the range of values. Color equals red, type equals L. Anyway, this gives you a chance to actually look at the polynomial fit there, which you can compare to what we fitted previously. Okay, it's a little bit complicated, but I think it's worth doing. Okay, it's not part of the exam question, that's for sure, because it's a little bit more tricky than one would expect. Yeah, so just screenshot it and try it out yourself. Okay, we'll leave it there.